A modern web browser operates as a highly sophisticated black box execution engine. It pulls down opaque payloads and compiles these instructions within your system's memory. This architecture is deliberate. Developers build these environments to process thousands of background network transactions, like fetching data, validating security keys, and rendering frames, all entirely hidden from the user interface. Inspecting the source of a streaming video often reveals a blob URL. This URL acts as a local pointer, indicating that a massive object has been constructed dynamically inside your RAM. Engineering the browser to work this way allows streaming platforms to protect copyright. By compiling video chunks in an opaque memory space, they prevent users from simply right-clicking and saving a raw media file. Creating an environment explicitly designed to execute hidden, memory-resident payloads introduces a severe vulnerability. This exact execution pathway provides the primary attack surface for a drive-by compromise. Mastering the browser's network tab and its execution pipelines provides the visibility required for both extracting protected data and hunting advanced persistent threats. Consider a standard forensic scenario. You open your developer tools, inspect the document object model, and locate a video tag locked behind a source attribute starting with blob:/HTTPS. This diagram illustrates how a binary large object, or blob, functions. It is an isolated cluster of raw binary data allocated strictly within the browser's local RAM, separated from the external network. To display that data, the browser calls the url.createObjectURL function. This maps the invisible memory sector to the visible HTML video element on your screen. Because the document inspector only shows the final mapping, discovering how that binary data entered the RAM requires monitoring the traffic hitting the network tab. Filtering the network requests allows you to track the initial handshakes. The process typically begins by fetching a JSON master file containing the initialization parameters and keys to start the stream. The master file points to an M3U8 playlist. As seen here, the playlist provides the roadmap for the media, dictating the specific sequence of individual chunk URLs that form the full video. Through the HTTP live streaming protocol, the browser reads this playlist and continuously fetches small, encrypted binary chunks, feeding them directly into the memory space. The browser takes remote text instructions, fetches fragmented code, and actively compiles a functional payload on the client side. Modern hosting platforms actively block unauthorized extraction. If you copy that M3U8 URL into an automated script, the server will refuse to hand over the data. Before releasing the playlist, the server profiles the client. It forces the browser to execute obfuscated JavaScript challenges to prove the request is coming from an approved execution context. This flowchart represents the verification step. The server halts the request and demands a proof of origin token. If the client cannot generate the correct cryptographic response, the connection drops. Extraction frameworks like YT-LP navigate this by integrating custom plugins. These plugins intercept the server's demand, synthesize the required token by simulating a valid browser environment, and pass it back to unlock the stream. Platforms deploy this verification layer to enforce digital rights management and prevent mass automated scraping, keeping their bandwidth allocated to legitimate human viewers. This demand for execution proof forces the client to run specific code on its local machine before the server authorizes payload delivery. Once the network chunks clear the verification phase and enter the local memory, the fragmented data must be mathematically reconstructed into a functional file. This pipeline represents the FFmpeg architecture. The data enters a Demuxer, which separates the interleaved data into distinct channels for video and audio packets. Those compressed packets pass through a decoder. The decoder translates the data into a continuous sequence of raw, uncompressed frames and PCM audio. At this stage, the data passes through a filter graph layer. This is where the client applies any necessary transformations, scaling resolutions, or overlaying visual elements directly onto the raw frames. Finally, an encoder recompresses the frames, and Demuxer interleaves the audio and video back together, writing the bytes into a finalized MP4 container. The video is dynamically fetched, compiled, and reconstructed from raw remote instructions entirely within the client's own environment. Advanced persistent forensics weaponize exactly the same system. The dynamic compilation architecture built to assemble media streams is the exact mechanism used to bypass enterprise security. In threat intelligence, this technique is tracked as MITRE ATT&CK T1189, drive-by compromise. It exploits the browser's natural tendency to execute fetched code automatically. Instead of targeting the user with phishing emails, attackers compromise a legitimate website heavily trafficked by their target demographic, a watering hole. The site silently serves malicious scripts instead of a standard media player. This diagram compares the two flows. On the left, a media server challenges the client for a proof of origin token. On the right, a malicious watering hole server forces the browser to run a profiling script, silently fingerprinting the user's operating system, plugins, and patch levels. Groups like North Korea's APT-37 use tools like Rice Curry to perform this analysis in the background until it locates a specific vulnerable plugin. Once a vulnerability is confirmed, the attack mirrors the streaming video process. Just as an M3U8 playlist feeds video data, the compromised server dynamically delivers the exploit shellcode in obfuscated, encrypted chunks. These chunks are reassembled directly within the browser's RAM, bypassing the hard drive entirely. Traditional perimeter defenses and signature-based scanners rely on analyzing files written to disk. Because this exploit delivery matches the browser's intended memory-resident dynamic architecture, legacy defenses see only normal web traffic. If a zero-day exploit mimics a legitimate media fetch, how can a security operations center actually detect it? Detection requires correlating anomalous network traffic with highly specific, atypical execution behaviors on the endpoint. This timeline maps the MITRE detection analytics. First, proxy logs show a request fetching an obfuscated JavaScript resource from an uncommon domain. Second, on the endpoint, the browser process suddenly spawns an unexpected child process, like an interactive Unix shell. Third, a dense cluster of rapid file drops occurs immediately after. Observing an obfuscated script or a new temporary file in isolation will generate false positives. However, observing these three distinct events in precise chronological sequence identifies a drive-by compromise. Opaque, memory-resident execution is the immovable bedrock of the modern web. Deconstructing these pipelines, mapping the flow to memory allocation, is the only way to intercept protected data and the advanced threats hiding inside it.